Greetings, I'm Salvador Cordova. Welcome to Lecture 1.5 entitled Measurement Uncertainty, Accuracy, and Precision in this college-level general chemistry lecture series presented by the Evidence Reasons Academy. Thank you for joining me today. For all those who have been a part of watching this series so far, I salute you for your commitment to learn. The last lecture and this lecture are tedious technicalities in understanding measurements. Kudos to all of those who endured the last section and will endure this section. With that, let's dive right into lecture 1.5 entitled Measurement Uncertainty, Accuracy, and Precision from OpenStax. (1.5) Measurement, uncertainty, accuracy, and precision. By the end of this section, you will be able to define accuracy and precision, distinguish exact and uncertain numbers, correctly represent uncertainty in quantities using significant figures, apply proper rounding rules to computed quantities. Counting is the only type of measurement that is free from uncertainty, provided the number of objects being counted does not change while the counting process is underway. The result of such counting measurements is an example of an exact number. By counting the eggs in a carton, one can determine exactly how many eggs the carton contains. The number of defined quantities are also exact. By definition, 1 foot is exactly 12 inches, 1 inch is exactly 2.54 centimeters, and 1 gram is exactly 0.001 kilogram. Quantities derived from measurements other than counting, however, are uncertain to varying extents due to practical limitations of the measurement process used. Significant figures in measurement. The numbers of measured quantities, unlike defined or directly counted quantities, are not exact. To measure the volume of liquid in a graduated cylinder, you should make a reading at the bottom of the meniscus, the lowest point on the curved surface of the liquid. Well, let's look at that. Figure 1.26. To measure volume of liquid in this graduated cylinder, you must mentally subdivide the distance between the 21 and 22 milliliter marks into tenths of a milliliter, and then make a reading estimate at the bottom of the meniscus. Tenths of a milliliter. Oh, what would that be? That looks like 0.75 between the 21 and the 22 milliliter marks. Actually, that 21, okay, so this is 21 and this is 22. That looks like 22.75. That's my estimate. Let's just move forward. Refer to the illustration in figure 126. The bottom of the meniscus in this case clearly lies between 21 and 22 markings, meaning the liquid volume is certainly greater than 21 but less than 22. The meniscus appears to be a bit closer to the 22 ml mark than to the 21 ml mark. And so a reasonable estimate of the liquid's volume would be 21.6. Okay, so I was off. In the number 21.6 then, the digits 2 and 1 are certain, but 6 is an estimate. Some people might estimate the meniscus position to be equally distant from each of the markings and estimate the 10th place digit as 5, while others may think it to be even closer to the 22 milliliter mark and estimate this digit to be 7. Note that it would be pointless to attempt to estimate a digit for the 100th place, which I just did. Apologies to the reader. Given that the 10th place digit is uncertain, In general, numerical scales such as the one on this graduated cylinder will permit measurements to 1/10 of the smallest scale division. The scale in this case has a 1 milliliter divisions, and so many volumes may be measured to the nearest 0.1 milliliter. The concept holds true for all measurements. Even if you do not actively make an estimate, if you place a quarter on a standard electronic balance, you may obtain a reading of 6.72 grams. The digits 6 and 7 are certain, and the 2 indicates that the mass of the quarter is likely between 6.71 and 6.73 grams. The quarter weighs about 6.72 grams, with a nominal uncertainty in the measurement of plus or minus 0.01 gram. If the coin is weighed on a more sensitive balance, the mass might be 6.23 grams. This means its mass lies between 6.22 and 6.24 grams, an uncertainty of 0.001 gram. Every measurement has some uncertainty, which depends on the device used and the user's ability. All of the digits in a measurement, including the uncertain last digit, are called significant figures or significant digits. Note that 0 may be a measured value. For example, if you stand on a scale that shows weight to the nearest pound and it shows 120, then the 100s, 10s, and 0s, ones, are all significant measured values. A measurement result is properly reported when its significant digits accurately represent the certainty of the measurement process. But what if you were analyzing a reported value and trying to determine what is significant and what is not? Well, for starters, all non-zero digits are significant, and it is only zeros that require some thought. We will use the term leading, trailing, and captive for the zeros, and we'll consider how to deal with them. Starting with the first non-zero digit on the left, count this digit and all remaining digits to the right. This is the number of significant figures in the measurement, unless the last digit is a trailing zero lying to the left of the decimal point. I don't think they worded that as nicely. This is the number of significant figures in the measurement unless the last digit is the trailing zero lying to the left of the decimal point. Starting with the first non-zero digit on the left, so that would be 3 in this case. Count this digit and all remaining digits to the right, 1, 2, 3, 4. Unless the last digit is a trailing zero lying to the left of the decimal point. So this would be counted as 3 significant figures unless, and I should point this out, unless you're given some other information to tell you that it is. There are special cases of this. Excuse me, it's kind of obnoxious. It does that every now and then. And I don't think, unfortunately, they explained this one, but we'll just keep moving and see if we can find it. Captive zeros result from measurement and are therefore always significant. Leading zeros, however, are never significant. They merely tell us where the decimal point is located. Okay, so this is a leading zero, and so it's saying it's not significant. The captive zero that's caught in between 2 non-zero numbers is significant. In the case here, the trailing zero is significant because that zero is behind the decimal point and it is a trailing zero. So a trailing zero behind the decimal point is significant. I think they could have expressed that a little bit more clearly, but we'll just try to work with it. Intuitively, we sort of learned this. Okay, first non-zero figure on the left, and so this is 4 significant figures, 1, 2, 6, 7, and measurement is in meters. This one is first non-zero figure on the left, and then a zero, a trailing zero on the right. Okay, I should point out something. When it says leading zeros, however, are never significant, it's never significant if it's a leading zero if there is no non-zero number here. If it is 0 in front of the decimal point, then these are all leading zeros in this case. Okay, so let's count. First non-zero figure on the left, 7, 0. So that's 1, 2, 3, 4, 5. Oh boy, that's obnoxious. It just keeps 1, 2, 3, 4, 5. Significant figures are measured including the 2 zeros, because this 0 is, I guess you could say technically it's captive because it's between 2 non-zero numbers, even though one of the numbers is on the other side of the decimal point. And this is also a captive 0 because it's between 2 non-zero numbers. In this case, these first 3 zeros are leading zeros. So the 0 to the left of the decimal point is the value 0 and no non-zero numbers. And then to the right, immediate right of the decimal point are 2 zeros. Those are leading zeros. So we disregard those. So the first non-zero figure on the left is the 8. And we have 1, 2, 3, 4, 5, 6 significant figures. The leading zeros in this example are not significant. What's kind of unfortunate is they're not making it really clear what diagram they're referring to. It looks like they're clearly referring to this diagram. We could use exponential notation as described in Appendix B and express the number as 8.32407 times 10 to the minus third. Then the number 8.32407 contains all of the significant figures. And 10 to the minus 3 locates the decimal point. The number of significant, okay, this is the exception here, and I'd like to point it out. That's what I was alluding to. There's this kind of this exception. The number of significant figures is uncertain in a number that ends with a 0 to the left of the decimal point location. The zeros in the measurement of 1,300 grams could be significant, or they could simply indicate where the decimal point is located. The ambiguity can be resolved with the use of exponential notation. 1.3 times 10 to the third is 2 significant figures. 1.30 times 10 to the third is 3 significant figures if the tens place were measured, or 1.300 times 10 to the third, 4 significant figures if the ones place was also measured. In cases where only the decimal formatted number is available, it is prudent to assume that all trailing zeros are not significant. So that's just the assumption. They're just saying, just assume that, unless, that's what I was saying, unless otherwise noted, that's how you would count it. And I was referring to this example here where it's not exactly clear, but we'll just assume it's only 3 significant figures. They could have implemented the examples and text description just a little better, but we can work with it. I'm just going to peruse this over. Okay. I wanted to go back to this sentence. It says the 1 is the 100, so there's 100. 2 is the 10, so there are 2 10s, so that's 20, and 0 ones. Okay. Okay. Here's an example. This scale measures to the nearest pound, so we actually have information that's telling us it's measuring to the nearest pound. So this 0 is significant. But in this case, if we didn't have any other information, we would assume it's not significant. So that is one of the problems there. So just be aware of it. And just to emphasize again, in this case, we have some challenges. We have the significant figures for sure, which is 1 and 3. The zeros, these zeros could be significant measured, or they could be placeholders. We don't know unless we're provided other information. When determining significant figures, be sure to pay attention to the reported values and think about the measurement in significant figures in terms of what is reasonable or likely when evaluating whether the value makes sense. For example, the official January 2014 census was reported to the resident population of the U.S. as 317,297,725. Do you think the U.S. population was correctly determined to the reported 9 significant figures? That is, to the exact number of people. People are constantly being born, dying, or moving into or out of the country, and assumptions are made to account for the large number of people who are not actually counted. Because of these uncertainties, it might be more reasonable to expect that we know the population to be within perhaps 1 million or so, in which case the population should be reported as 3.7 times 10 to the 8th people. Yeah, that's true. All those illegal aliens coming in, I know. That could skew the figures. Significant figures and calculations. A second important principle of uncertainty is that results calculated from a measurement are at least as uncertain as the measurement itself. Take the uncertainty in measurements into account to avoid misrepresenting the uncertainty in calculated results. One way to do this is to report the result of the calculation with the correct number of significant figures, which is determined by following 3 rules for rounding numbers. When adding or subtracting numbers, round the result to the same number of decimal places as the number with the least number of decimal places, the least certain value in terms of addition and subtraction. When multiplying or dividing, round the result to the same number of digits as the number with the least number of significant figures, the least certain value in terms of multiplication and division. If the digit to be dropped, the one immediately to the right of the digit to be retained, is less than 5, round down and leave the retained digit unchanged. If it is more than 5, round up and increase the retained digit by 1. If the dropped digit is 5 and it's either the last digit in the number or it is followed by zeros, round up or down, whichever yields an even value for the retained digit. If any non-zero digits follow the dropped 5, round up. Okay, so really practice will help you do this. It's kind of hard to just kind of think of this in the abstract. It's better to practice through it. You'll see it. It's not that bad. You'll be able to do this very intuitively. The last part of the rule may strike you as a bit odd, but it's based on reliable statistics and is aimed at avoiding any bias when dropping the digit 5, since it is equally close to both possible values of the retained digit. The following examples illustrate the application of this rule in rounding a few different numbers to 3 significant figures. Okay, so let's count how many significant figures. We have 28675. I mean 0.028675. That's 5 significant figures. And so we're going to drop these 2 figures. So we're going to round up to 0.0287. And we're going to round to 3 significant figures. So it should be 183. Is that 3? Yeah, so the rest here is less than 5. This number is less than 5. So we just drop it. So it should round down to 1.83. The drop digit 3 is less than 5. 6.8752 rounds up to 6.88. That's because the drop digit is 5 and a non-zero digit follows it. $9,285 rounds down to 92.8. The drop digit is 5 and the retained digit is even. So just practice this. The rules will start to sink in. Let's work through these rules with a few examples. Rounding numbers. Round the following to the indicated number of significant figures. Round to 2 significant figures. Maybe I should put, I'm going to try this. I'm going to try to put a, I'm going to try to put a little PowerPoint slide here so we could just practice this, and I can color a few things. Let's see. It's going to be a little obnoxious here. Please bear with me. 31.57. So I think what I'll do is I'm going to colorize some parts. And I won't, in the interest of time, I don't think I can do this for everything, but we'll try to do a little bit anyway. So I put in yellow, it says process round the following to the indicated number of significant figures. So we want to just have these 2 positions retained. And I'm going to put a, there is a sign here. See symbol. And I want this little approximate symbol. So that's approximately 3, 2. So I round, so we have the 5 here. And because it's followed by a non-zero digit, we round up. So I rounded up to 3, 2. So let's do 8.1649, and it wants 3 significant figures. And I'll show the positions there. I'll colorize it. And I'll also, it's approximately 8.16. Since this number is less than 5, we'll just drop it. We'll drop that in the rest of the figures, and it's 8.16. Hopefully you could see that. Let me make this even larger. I can afford to do that. Okay, let's look at the next number. 0.051065. $0.051065. So 0 is the number to the left of the decimal point, and there are no non-zero numbers to the left of the decimal point. and immediately following the decimal point is a 0, and that's considered a leading 0. So it says it wants it to 4 significant figures. Just let me clean that up a little bit. So 4 significant figures. So the first significant figure starts there, and then the next one is there. And according to our rules, if this is rounded up, we drop. I mean, if it's a 5 followed by no non-zero numbers, I mean, if we're going to get rid of this 5, and it's followed by no non-zero numbers, the rule is, let me just verify that. Okay, round up or down, whichever yields an even number for the retained digit. So we want to retain the digit, and it has to be an even number. So 0, 5, 1, 0, 6. And just to color code things a little bit, I'm going to color code the significant figures. Let's do this one. 421.25, 4 significant digits. Let's see. 421.25, and they're 4 significant digits. So we start from the left and go right. I'd like to say learning how to do this is almost like walking. It's better to do it, and then you just sort of know it intuitively. That's about the best way I could describe it. Yes, it's good to go through the rules, but at some point, it just starts to be kind of like a reflex, just the learned behavior. You don't even realize you're doing it. So it says here, wants 4 significant digits. And so the number we drop will be 5 here. This 5 here that I just highlighted in gray. And in that case, if it is 5 and it doesn't have any non-zero numbers after it, we either round up or down the digit we're going to retain. The digit we're going to retain is this digit here in this position where I just highlighted the yellow with gray. And we want to retain, we round down if the number is even, we round up if it is odd to make it even. So 421.2. And then finally, we have 28,683.5 and 5 significant figures. So we just start from the left and we go to the right. There are actually 6 significant figures. It wants it to round it to 5. I mean, there's 6 figures in the measure in this figure, and it only wants 5 significant figures. And so it should be, so the first 4 numbers are easy, 2, 8, 6, 8. The last one, the last significant figure is the one in question. So the number we're going to drop is 5. Since it has no non-zero numbers after it, we round up, because when it's a 5, and in that situation where there's no non-zero numbers after it, we either round up or down, but we want to round up or down in a way that we get a even number. So in this case, if it is a, if the odd number would otherwise, in this case, if we rounded down, we would get a odd number. If we rounded up, we would get an even number, and we want an even number. So let me verify that that's what I'm supposed to do. So let's verify the answers. A was, whoa, where did I see this? Where did I get 31.57? Apologies. Okay, panic there for a little bit. Okay, so this should, here are the solutions. I got 32. This one said 8.16. What did I get? 8.16. The correct answer here is that. Oh, I missed the 0 here. Sorry. My mistake. And apparently I got a little lost here when I was navigating. I solved the wrong problem. My apologies to the readers. So I'm going to have to try to do this. 0.90275. 0.90275 to 4 significant digits. So these are the significant digits there. And you can see I'm fumbling through this. That happens. And it wants 4 significant digits. In this case, we're supposed to round. We have the number we're going to drop is 5, and it doesn't have any numbers after it. So we either round up or down. We want to, if we round down, it will have the last retained digit. The last retained digit is the digit in this position that I'm highlighting in gray. It'll be odd, and that's not what we want, so we will round up. So 0.90275. 27, I'm sorry. We want to round up, so it should be an 8. And it says 0.9028. Okay, this was good for me because I was being a little bit sloppy. And we'll just keep moving. So I will make another. All right. Okay, so let's try. I shouldn't show the answers by accident. They're there. I mean, there's no cheating here. Everything that that I'm going through is available in OpenStax. So let me borrow a piece from here. So I'll just save that piece for later. So just to be a little bit clearer, we're on question A. And let me increase the font. So question A, we have the original number 0.424, and we round to 2 significant digits. So in the original number in the original figure, we have three figures, but we're only going to retain these two highlighted in yellow as the significant figures. Oh, excuse me, let me correct this. And so let's round it. The number we're going to dispense with is here, and anything thereafter is below 5, so we round down, and the number will be 0.42. And let me highlight that with yellow. Okay, so example B is 0. Let me turn off that highlighting. 0.0038661, and it wants it to be only 3 significant figures. And I'll highlight that. So I'll explain again. The value to the left of the decimal point is 0. And then now what we can say, since it's to the left of the decimal point, then any zeros immediately to the right of the decimal point are leading zeros. So and that'll be the, so every 0 is leading until one encounters a non-zero number. So now we can begin counting the significant figures from this location. That's what I did in the highlight. And it wants 3 significant figures. So 0. So we include the original leading zeros. And since those aren't, we're still supposed to do that, even though they're not significant figures, you need to include them. And then the 3 and the 8 are guaranteed there. So the question is what we do with the 6. Whether we retain it as a 6 or not depends on this number, which is the number we're going to drop, and then any number to the right of it. And so, since that's a 6, we round this number up to 7, I'm sorry. Up to 7. Then this is C, 4 to 1.25 to 4 significant figures. So let's see what the significant figures are. We start on the left and we keep going right, even past the decimal point. So the question is, definitely 421 is set. We're not gonna, we don't have to do any rounding. It's the last significant figure we may or may not have to do, but we have to make a decision how to round it. Since the first number that we drop, since the first non-significant figure that we drop is a 5, we either round up or down. And the rule is we round down if the last digit, the last significant figure is even. We would round up if it's odd. So following those rules, we get that. And I accidentally already did D. So let's see the answers. Say first answer is 0.42, which I got. Next answer is 0.00387, which I got. And C is 421.2, and I got that. And D is 28684, and I got that. Okay, thank you for bearing with me. The practice will make perfect on this. This can be, as I said, this is going to be kind of tedious. And oh my, we have more to go. I'm just perusing how much we're. This is like, yeah, I told you this is going to be some tedium here. This is enormous amount of tedium. So we're just going to suffer through it together. This is considerably more challenging to teach than the last four sections. So let me just take a little breather here. Okay, addition and subtraction with significant figures. Rule: when adding or subtracting numbers, round the result to the same number of decimal places as the number with the fewest decimal places, the least certain value in terms of addition and subtraction. So let's add 1.0023 grams and 4.383 grams. And there's a solution there. And you can see that they add it. And when one gets the addition, their fonts are a little bad. You see the decimal places are not aligned. It's not very clear. Sorry, that's just a pet peeve. The proper way to round it is we round to the thousandths place, the 3 decimal places. So what they're saying is, let's just look at the rule. When adding or subtracting numbers, round the result to the same number of decimal places as the number with the fewest decimal places, the least certain value in terms of addition and subtraction. And so the number with the least number of decimal places is this number, 4.383. So we're just going to round to 3 decimal places. And that was, and so the result is 5.385 because we're just going to drop the 3 as part of our rounding procedure. Now let's look at this example here. B, 421.23. We're going to subtract that from 486. And 486, we're going to subtract 421.23 from 486. The answer is 65 grams, round to the ones place. So even though, yes, so there's nothing after the decimal here, so we don't have any figures beyond the decimal point. So there's 0 numbers beyond the decimal point, and we should round according to that rule. Then we get 65 grams. And they're trying to illustrate it here, how this is done. Notice in their diagram, they actually have the decimal points aligned. Just a little complaint there. All right, so let's check our learning. And I might need to, in order to do this, bring up a spreadsheet calculator, and I'm going to do that right now. So it says here, add 2.334 milliliters to 0.31 milliliters. Notice that there are only 2 numbers beyond the decimal point there. And I'm trying to bring up my spreadsheet, my spreadsheet calculator. So if please, if you can forbear with me for just a little bit. Okay, so let me erase this spreadsheet, get a new one. Let me get rid of this. I'll bring a new spreadsheet in. Make this smaller. So what do we have? We have 2.334, and we're going to add 0.31 to it. We get 2.644, but we're only supposed to have 2 decimal places. So let's round to 2 decimal places. And let me what number did I get? 2.644. 2.644. Let me make the font bigger. We only want to preserve 2 decimal places. Wow. We only want to preserve 2 decimal places. And so since the number we're going to drop is less than 5, this is, the answer is 2.64. We round down. Okay. Now the next one is subtract 55.8752 from 56.533. So let's do that. Just get another cell here. When it says subtract from, that means we can start off with 56.533 meters, and from it we'll subtract 55.8752. So let's see what number we get. So I'm going to take that number, and from it I'll subtract that number. We get 0.6587. But notice this number here has only 3 numbers to the left of the decimal, three positions to the left of the decimal point. Therefore, we're going to, let me just clean this up a little bit. So now let's do B. And the number is 0.6578. And again, note, we only want 3 numbers past the decimal point. Just according to our rules that we were given for doing subtraction and addition. So we retain 6, 5, and it's the 7, the last significant digit. We have to determine whether to round up or down, and because the digit immediately to the right of the last significant digit is an 8, we round up, therefore the 7 rounds up to 8. Let's check our answers. They got 2.64. Oh, I need to put the units. Milliliters, and the next one is meters. So let me clean this up a little bit. Apologies to the viewers. Meters, I'm sorry. Meters. Okay, I'll try to be a little bit cleaner next time. Multiplication and division. Example 1.5 in this section. Rule: when multiplying or dividing numbers, round the result to the same number of digits as the number with the fewest significant figures, the least certain value in terms of multiplication and division. So multiply 0.6238 centimeters by 6.6 centimeters. Let's see the answer. So when we multiply it, we put it in our calculator. And by the way, when you multiply the units too. So centimeter times centimeter equals centimeters squared. And then you multiply the number. The result needs to be rounded to two significant figures because the smallest, let's see, round the result to the same number of digits as the number with the fewest significant figures. Round the result, and that's the result, to the same number of digits as actually the wording is a little bit weak. Same number of digits. It should say round the result to the same number of significant figures as the number with the fewest significant figures. They didn't word that really well. Round the result to the same number of significant figures as the number with the fewest significant figures. So I'm just providing a little bit of correction there. I'm sorry, we have to be, I was a little sloppy and I missed a few things and they missed a few things too, so we're even. I'm getting really sleepy. It's terrible when your own lecture is boring you to death and the lecturer is falling asleep. So anyway, that's the answer. Okay, so now let's divide. Let's go to question B, example B. Divide 421.23 by 486. Divide 421.23 grams by 486 milliliters. So this is going to be actually a density calculation. And we could see there are 5 significant figures here and there are 4 significant figures here. So the smallest number of significant figures is 3. There are 3 significant figures here. So we'll just go ahead and punch it into a calculator. And notice you have to, one has to use the units grams divided by milliliters. So just leave that there. Since we want to have 3 significant figures, the result is 0.867 grams per milliliter, round to 3 significant figures. See, they have it here. 5 significant figures divided by 3 significant figures yields 3 significant figures answer. So let's check our learning. So what I'm going to do, yes, this homework is going through this tedious. You bet. You bet. This is I mean, it's tedious. It's not going to kill you. I mean, I don't think we're having, we're just having to spend time on this when we could do fun things like playing video games. So it's not a matter that you don't have the brain power. I often said a college education isn't a measure of how much you know, it's how much punishment you can take. Sorry. So, let me just set this all up here. I think, all right. So we're going to multiply 2.334 centimeters times, I use a star for times, 0.320 centimeters. Let me get my spreadsheet calculator out. So 2.334 and 0.320. Let's multiply that times that. 0.74688. 0.7. Okay, so 0.74688. And I'll just put dot, dot, dot to indicate there could be more, may or may not be more figures. I don't see any. Okay, no figures since it's not a division. Apologies. Now that should be, let me point out something. There are 3 significant figures here. That trailing 0 is significant, right? So there's 3 significant figures here. There are 4 significant figures here. So we use the number of significant figures. We take the number with the least amount of significant figures, and that tells us how many significant figures should be in the answer. So let me try to see how I could phrase this. The answer should have the same number of significant figures as the there's a term for these as the products of the 2 numbers. So you take the 2 initial numbers and they have certain number of significant figures. The one with the least number of significant figures gives you the number of significant figures that should be in your answer. There's probably a better way of saying this, and I was trying to think of it. So that's the first significant figure, the second, and we have one more. So should the 6 remain a 6, or should it be rounded up? Because the number adjacent to it, adjacent to the 6, adjacent to the last significant figure is 8. We round up, and so that should be a 7. Okay, let's do B. Divide 55. Oh, this is obnoxious. I have to turn off the coloring. Divide 5. Oh, I made a mistake here. Centimeters squared. Let me get that right. Centimeters squared. I have to use the superscript. And I'll turn off the highlighting. I'll turn off the highlighting again. I mean the coloring. So 55.8752 meters divided by 6.53 seconds. So this is some sort of velocity. And the number will be some number with lots of digits. So let me just say 55.8752 divided by 6.53. That divided by that. 98841. I got 0.9884167 and some more numbers, and that's meters per second, and it is approximately, so this number has 1, 2, 3, 4, 5, 6 significant figures, and this number has only 4. So we take the number, the number of significant figures, and the answer should be the number of significant figures in there's a term for either in the numerator or denominator. Apologies. the numerator or denominator with the smallest number of significant figures. The same number of significant figures as the number of significant figures in the number with the smallest number of significant figures. I'm sorry, I'm trying to think of a way to phrase it, but I just end up making it more confusing. So anyway, so since it's going to be 4 significant figures, the first 3 are really just a given. It's the 4th one that is uncertain. It's the 4th one that is uncertain. And in this case, the 4th number will be 4. Is it rounded up or down? And it is rounded down. So we just retain it as is, because the numbers to the right of it are less than, the number to the right of it is less than 5. So let's, oh, and I need to put the units. Let me not be sloppy. That is in meters per second. Yeah, this is what it takes to do it right. Just be slow and meticulous. Don't have to rush. When I played musical instruments, the professor said, just practice real slow. You'll be able to get speed very quickly. If you practice fast, you'll just make a lot of mistakes. You'll never gain any speed because you'll just be playing with lots of mistakes. You'll be learning how to, you'll be playing fast with lots of mistakes. Do it slow, and then you'll gain speed, and you'll be playing with less mistakes too. So anyway, let's check our answers. Answer A is 0.747 centimeters squared. Answer B is 0.9884 meters per second. I got it right. Okay. And what do they say? In the midst of all these technicalities, it is important to keep in mind the reason for these rules about significant figures and rounding, to correctly represent the certainty of the values reported, and to ensure that a calculated result is not represented as being more certain than the least certain value used in the calculation. So example 1.6, calculation with significant figures. One common bathtub is 13.44 decimeters long with 5.920 decimeters wide. Okay, one common bathtub is 13.44 decimeters long, 5.920 decimeters wide, and 2.54 decimeters deep. Assume that the tub is rectangular and calculate the approximate volume in liters. So volume is length times width times depth, D, okay, or deepness. And it calculated it. And that's the number that we get from the calculator. And since the number with the smallest number of significant figures is 2.54, and that number has 3 significant figures, that should be the number of significant figures in the answer. And so it is rounded to 202 liters. A decimeter cube is a liter. They could have put it decimeter cubes, or yes, that's it. A decimeter cube is a liter. A decimeter cubed is a liter. Okay, so let's check our learning. What is the density of a liquid with a mass of 31.1415 grams and a volume of 30.13 cubic centimeters? So let's just do a calculation here. Put this in my spreadsheet calculator, 31.1415. By the way, I love spreadsheets. It's a great way to do this, because if you make a mistake in a big calculation, you only have to correct that mistake. You don't have to punch the numbers in again into the calculator. So let me put so that's in grams and that's in cubic centimeters. So let's multiply. Nope, we want to divide. Density. Density is the mass divided by the volume. So that's the mass is in grams divided by the volume. And that should be grams per cubic centimeter. So we take each number, the numerator and denominator, and figure out which one has the least number of significant figures. And it is this number here that has 4 significant figures. That number of significant figures should be reflected in the answer. It should be the number of significant figures in the answer. So let me just, again, for completeness, and I'm sorry, this is just brutally tedious, but I'm doing it very meticulously here, just so hopefully people can think about it and I'm not rushing it through. And it also keeps me accountable so that I'm being reasonably accurate here. So what was our answer on the spreadsheet? Three 1.1415 grams. Let me make this larger. And we're going to divide by 30.13 cubic centimeters. Oh, I have to turn off that. Turn off the superscript. Apologies here, I'm having just I'm making a lot of typos here and I need to fix it. Equals 1.03357119. All right. And we want to round this to 4 significant figures. So that is approximately, so the first 3 numbers are fixed. It's the 4th one, and we have to decide whether to round up or down. The next number, we'll round up because the next number is 5, followed by non-zero numbers. So this should be a 4. And let me highlight the important figures here. So let's check your learning. The answer is, oh, and I need to put the right units. That would be grams per cubic centimeter. This may sound funny. I haven't done a lot of lab intensive work. And so sometimes most of my work has been away from the lab doing just calculations. And oddly enough, in physics, we have a lot of we assume a lot of natural units. And so sometimes when you have natural units, they actually don't have units. They're just one. It's like in general relativity or special relativity, sometimes they just drop the units. They just put 1. If you study relativity, general relativity, you'll understand totally what I mean. So I'm having to learn how to do this to be more meticulous. Now notice here, the answer is grams per milliliter, but a cubic centimeter is a milliliter. So let me, that may have thrown some people off, and I will just do the conversion here. 1.034 grams per milliliter. Let me colorize it, okay. And so let me just double check the answer. 1.034 grams per milliliter, excellent. Okay. Let me see how many more of these we have. Okay, we're still not quite at the end. We have to go through example 1.7. So we just did 1.6, 1.7. Experimental determination of density using water displacement. A piece of rebar is weighed and then submerged in a graduated cylinder partially filled with water, with results as shown. And the rebar mass was 69.658 grams. The final volume, 22.4. The initial volume, 13.5. Okay, the nice thing is they're doing the reading for us, because I messed up the reading before. So what does it want us to do? Use these values to determine the density of this piece of rebar. Rebar is mostly iron. Does your result in A support this statement? How? All right, so let's first calculate the density of this piece of rebar. First, I'll bring up my calculator. And we have, to calculate density, divide the mass by the volume. So the mass is 69.658 grams. The volume is 22.4 milliliters. Oh, that's wrong. We have to calculate the volume first. So the volume of the rebar is, we take the final volume minus the initial volume to determine the volume of the rebar. Does that sort of make sense? We take the volume in this cylinder here minus the volume in this cylinder here. That tells us the volume of the rebar. So 22.4 milliliters, and we have 13.5 as the initial. So you'll hear that often used. Subtract, take the final and subtract the initial, or subtract the initial from the final, and we'll do that. And that is 8.9 milliliters. We end up with two significant figures. All right, I think that's right. ml. So we divide 69.658 grams divided by 8.9 milliliters, and we get this number. And let me make a new slide. I'm just going to put the results here. 7.8 2674157 ... Okay. I'm just going to use the final result from the spreadsheet. I'm not going to type everything out, just partly in the interest of time. And the units are grams per milliliter. density. And we're only supposed to report 2 significant figures, because there are only 2 significant figures between the denominator and numerator. The number with the smallest number of significant figures is in the denominator, and that's 2 significant figures. So the answer should reflect that. And so the first number is a given. The second one depends, do we round up or down? And that depends on the number after the significant figure that we're keeping, the last significant figure we're keeping. And since it's less than 5, since the number after the last significant figure is less than 5, we round down. And so that should be 7.8 grams per milliliter. Rebar is mostly iron. Does your result support this statement? How? Okay. One way we can resolve this is to go to Google. Let's look up the density of iron. Density of iron. Density of iron is 7.86 grams per cubic centimeter. Remember, a cubic centimeter is a milliliter. And what number did we get? So they had 7.86 grams. We got 7.8. So we're just a little bit less dense than pure iron. I presume there could be some impurities or whatever. So rebar is mostly iron. Does your result in A support this statement? Yes, because it's close within. It's close. If we rounded the density of iron to 1 significant figure, it'd actually be 7.9. So this is just a little less dense. It's not, perhaps it's not pure iron, or there's something else in play. So let's see what the answer is. Solution: the volume of the piece of rebar let's see, I got 8.9 milliliters, rounded to the nearest 0.1 milliliters, and they got 7.8 grams per cubic centimeter, like I did. And I did round to the correct number of significant figures. From table 144, the density of iron is 7.9 grams per cubic centimeter, very close to that of rebar, which lends some support to the fact that rebar is mostly iron. Oh, okay. So there was a qualifier there. All right, here's another exercise. Check your learning. An irregularly shaped piece of a shiny yellowish material is weighed and then submerged in a graduated cylinder with results as shown. So we're going to do this whole thing again. Same idea. So we had practice the last time, we got it right, but that was tedious, but we'll do it again. I'm going to cheat a little bit here. I'm going to copy a template just so I could be a little bit quicker. So the mass is 51.842 grams. The final volume is 19.8. The initial volume 17.1. Okay, so final volume. So there are 3 places after there's 1 place after the decimal, and we only have 2 significant figures in the denominator. The numerator has 5 significant figures. So the final result should only have 2 significant figures. So I'm just going to just use this template here. And the number we have is something like 19.200. And that would be grams per milliliter, and that is approximately, oh, let me back up. We only want two significant figures. So this will be approximately 19 grams per milliliter. I did this all in my head. I'm not doing it in brutal detail like the other examples. Hopefully you'll see that by now. So I get 19 grams per milliliter. Let me just double check that I did everything right. 19.8 minus 17.1 is 2.7, 2.7 milliliters, 5.1, 51.842 grams. Okay. Use these values to determine the density of this material. The density I get is 19 grams per milliliter. Do you have any reasonable guesses as to the identity of this material? Explain your reasoning. That's very dense. And one of the densest material is gold. The density of gold is 19.3 grams per cubic centimeter, or cc, which is also a milliliter. And I would identify this substance as gold. And oh, by the way, there's a little hint here. Even in the diagram, what color is the substance there? It's gold. The answer is 19 grams per cubic centimeter, or 19 milliliters. It is likely gold, the right appearance for gold, and very close to the density given for gold in table 1.4. And also, I use Google to get me the density of gold. I was lazy. I wasn't looking at table 1.4. So finally, I think we're at the end here. Accuracy and precision. Scientists typically make repeated measurements of a quantity to ensure the quality of their findings and to evaluate both the precision and the accuracy of their results. Measurements are said to be precise if they yield very similar results when repeated in the same manner. A measurement is considered accurate if it yields a result that is very close to the true or accepted value. Precise values agree with each other. Accurate values agree with the true value. These characterizations can be extended to other contexts, such as the results of an archery competition, figure 1.27. So we have an illustration here of accurate, because it's close to the bullseye. This one is precise but not accurate, so the archer is hitting kind of in the same location. And this is not accurate, not precise. It's not precise because the arrows are landing far apart from each other, and it's not at the bullseye. So that was figure 1.27. So, oh, why don't I just read the caption? Figure 1.27. A, these arrows are close to both the bullseye and to one another, so they are both accurate and precise. B, these arrows are close to one another but not on target, so they're precise but not accurate. C, these arrows are neither on target nor close to one another, so they are neither accurate nor precise. Suppose a quality control chemist at a pharmaceutical company is tasked with checking the accuracy and precision of 3 different machines that are meant to dispense 10 ounces, 296 milliliters of cough syrup into storage bottles. She proceeds to use each machine to fill 5 bottles and then carefully determines the actual volume dispensed, obtaining results tabulated in table 1.5. So it's supposed to be 296 milliliters. Volume, milliliters of cough medicine delivered by 10-ounce 296 milliliter dispensers. So dispenser 1, let's see, you want close to 296, 283. 284.1, 283.9, 284, 284.1. Okay, to do this really well, it's good to be able to just put this through a statistical package that'll give you mean and variance. And I'm really tempted to do that. Let's see if they give an explanation. Considering these results, she will report that dispenser 1 is precise, values all close to one another within a few tenths of a milliliter, but not accurate. None of the values are close to the target value of 296 milliliters, each being more than 10 milliliters too low. Results for dispenser 2 represent improved accuracy. Each volume is less than 3 milliliters away from 296 milliliters, but worse precision. Volumes may vary by more than 4 milliliters. Finally, she can report that dispenser number 3 is working well, dispensing cough syrup both accurately, all volumes within 0.1 milliliter of the target volume, and precisely, volumes differing from each other by no more than 0.2 milliliters. So this one's the hero right here. Yeah, I should have seen that. It's just getting late at night. And that is it. Oh my goodness, what a miserable session. And I thank all of those who have suffered through all this with me. And kudos to you for hanging in there. So there will be a separate exercise section, as if we didn't get enough exercise with this. There'll be a separate video that goes through the relevant exercises. So I think this was good material. I had a chance to practice some skills I hadn't used in a while. And so this is great. So thank you all for joining. Take care and God bless you.